Good morning, good afternoon, everyone. Thank you all for being here today for the inaugural lecture of the International Seminar on Quantization, Geometry and Dynamics, ISQGD. It is a great pleasure and an honor to have you all with us today. I would like to begin with a brief introduction to ISQGD, its purpose, its vision, and its goals. ISQGD is established as a global platform for a meaningful mathematical exchange, bringing together researchers working across a wide and interconnected spectrum of fields. These fields include quantization theory, fractal geometry, dynamical systems, ergodic theory, operator theory, geometric analysis, geometric measure theory, optimal transport, variational methods, geometric optimization, and many related fields. Our aim is to connect communities that often work independently and to create a shared space where ideas can flow freely across these disciplines. The main objectives of ISQGD are the following: to host regular research lectures delivered by distinguished experts from around the world, to foster an international mathematical community by encouraging interaction, collaboration, and the free exchange of ideas, to support future initiatives such as thematic workshops, mini courses, special lecture series, and outreach activities that help broaden the reach and deepen the impact of these research areas. The vision of ISQGD is to develop a seminar series that is open, inclusive, and intellectually vibrant, one that welcomes senior researchers, early career mathematicians, and students alike. Our hope is that ISQGD becomes a sustainable platform that promotes collaboration, inspires new directions, and contributes meaningfully to the future development of mathematical research. I am sincerely grateful to all of you for your support and participation. The growth of ISQGD will depend on the enthusiasm of its global community, and I truly hope this seminar series will flourish for many years to come. I also extend my sincere thanks and gratitude to the School of Mathematics and Statistical Sciences at the University of Texas Rio Grande Valley for hosting ISQGD and for their continued support. With that, I would now like to invite Professor Sergey Grigoryan, the Director of the School of Mathematics and Statistical Sciences at the University of Texas Rio Grande Valley, to share a few words and to introduce our inaugural speaker. Thank you.
All right, well, thank you, Dr. Rachaudhuri. And first of all, I'd like to thank you for organizing this and bringing everyone together. It's a great initiative, and thank you everyone for joining us today. So I also hope that this will become a forum where ideas can be exchanged and we can have great talks and great speakers. So we're looking forward to seeing this initiative flourish, and hopefully this will expand beyond just online seminars, but to workshops and other events. All right, so today it is a great pleasure and honor to introduce Professor Palle Jorgensen, our inaugural distinguished speaker. So Professor Jorgensen is an internationally renowned mathematician whose pioneering work on harmonic analysis, operator theory, wavelets, and fractal geometry has had a profound and lasting influence on modern analysis and mathematical physics. Professor Jorgensen is a long-standing member of faculty at the University of Iowa. He has mentored numerous mathematicians and produced an extraordinary body of research work. So it's marked by depth, originality, and far-reaching impact. So in fact, in Maths.net, he has over 400 papers indexed.
Where do I order the cups? A large coffee cup. Yeah. Thank you.
Sorry, could you just mute your microphones? Thank you. All right. So in fact, on MathSciNet, Professor Jorgensen has over 400 papers listed with over 4,000 citations, which shows a very impressive body of work. So it's a great honor to have him open this seminar series. Also, we thank Professor Jorgensen for agreeing to serve as the president of the ISQGD advisory and governing body, and we're grateful for his leadership and support in shaping the future direction of this initiative. So today, Professor Jorgensen will speak on harmonic analysis, frames, and algorithms for fractal IFSL2 spaces via infinite products of projections. So he will present new developments at the crossroads of operator theory, fractal harmonic analysis, and iterative algorithms for infinite dimensional structures. Please join me in welcoming Professor Palle Jorgensen. So, thank you.
Thank you very much for your kind words, and I'm very honored to be here and pleased to meet everyone again. And now I think I should get my share going here. So am I okay with permission? Should I just click share now?
Yes.
Okay, I'll do that, and I'll do that. And so now it should be here, and then I do Control L. Okay, so maybe I'll do it. Okay. So is
First,
what?
I'm sorry to bother, but first click on the screen and then put Control L.
All right.
Then it will go.
Yes. Okay, so now that's better. Thanks very much. Yeah, please give me tips because they're all surprises. All right, so to begin with, I'll just we can read the two lines that make up the title, and I'll explain them a little bit, mainly so that you can appreciate how they, in fact, connect to all of the items in the list that Mainal mentioned a few moments ago. But I want to narrow down a little bit. When I say harmonic analysis, I refer to Fourier frequencies. However, harmonic analysis has been used in the classical setting for an interval or higher dimensional spaces, in the case where the measures in one variable is the Lebesgue measure and higher variable Lebesgue measure built on each coordinate. But the new direction here comes from the occurrence of special attractors or special fractals or special limits, and the limits come up in dynamics, and the limits can often be modeled by a finite system of maps with a contractivity property that generates fractals with gaps. And not only do they generate the pictures you're looking at, you can also scale the starting measure and then get a limit fractal measure. And these limit fractal measures are often referred to as an IFS measure. The simplest, of course, come from Cantor sets and Cantor measures. If you do the middle third Cantor, then you can construct an increasing function, sometimes called the Devil's staircase, that increases just on the parts that are not deleted in each step, and that is then a Stieltjes measure for a Cantor measure. But you could also look more generally at a system of contractive maps, and you can turn that into an operation on probability measures, and you can show that probability measures can be made into a compact metric space, and then use a fixed point theorem to get existence of a very general family of IFS measures. The particular approach that I will take here deals with the second line, where I built the Fourier framework using a system of projections And so when I say projections, I refer to a Hilbert space, but in most of the cases that I'll be looking at, the Hilbert space will arise as an L2 mu, where mu is one of these measures, IFS measures, that we talked about. So you see that the second line emphasizes the role Hilbert space plays. And of course, all the L2 mu measures are Hilbert spaces, but they're very different as you move around with different choices of these measures. And so this one here is writing out a summary of what we just talked about. The only thing that I didn't mention on the slide here is an algorithm that we, in my joint work with co-authors that I'll mention shortly, we call it a CASMA algorithm because it's inspired by an algorithm that's popular in finite dimensions, but the basic idea that goes into the finite dimensional case is adapted to projections in infinite dimensional Hilbert space with special emphasis on the case where the Hilbert space is L2 or mu. Okay, and then the probability spaces would play an important role, and these harmonic analysis structures that we create turned out themselves to have a probability framework, so we can talk about some properties of dynamical fractals that apply for almost all with reference to a probability space. So that's one of the things that comes up as we continue here. And so this one here is the first technical slide that reminds us of what we're doing. And for some of the discussions, we make use of the geometry of a general Hilbert space. And in these discussions here, the Hilbert space we work with will be infinite dimensional, but when we build a Fourier system, then we of course use one dimension for each Fourier basis function, or if there's a finite number of them, then we use subspaces with specified with a finite number of frequencies. And so one of the things that goes into this is how many frequencies do we need to do Fourier, and what do they look like, and so on and so forth. And I think that, right, and so I mentioned that we will build the algorithms here making use of Hilbert space, in particular iteration of projections and infinite products of them, and I'll get to that shortly. Please stop me and ask questions if there are any questions at all. So that was the Hilbert space and the IFS, and then I go to the next one here. So this one, the top should just be a reminder in the classical case of Lebesgue measure that we have an interval like this. There are two popular choices of length 1 or length 2 pi, and that means that if it has length 1, then your Fourier frequency is e to the I 2 pi n dot x, and in the other case you don't need to put in the 2 pi in the Fourier functions, and n would refer to a Fourier frequency. And when I write n with a subscript 0, that means the positive numbers including 0. And so the first thing that I want to stress here, it's theorem 1, and it's sort of a corollary of the classical F and M Ries. But the purpose of that is the following. We all know that for Lebesgue measure and Fourier expansions that we've been using in solving PD for hundreds, well, a very long time, then we need all the frequencies. So if we normalize, we need all the integers. But for these fractal measures here, typically we only need the positive frequencies. And but I normalize that includes 0. But when I say positive from now on, I allow 0 as well. Okay, and so a singular is relative to Lebesgue measures, so that those include Cantor measures. So it says that two measures are singular if there's a partition of the space, so that in disjoint pieces, so that each measure is is supported on each of the disjoint pieces. That's called mutually singular. And as you know, that can be re-expressed in many other ways, for example, using radical negative derivatives. And we'll get to that when we need it. Okay, so the first example started with Cantor constructions, and then this is some work that I started a long time ago, identifying specific subsets of the positive integers that give us a Fourier basis for specific fractal. And so what this theorem here is saying is that all singular measures, whether they come from IFS measures or not, all singular measures, so that mutually singular, they have the Fourier frequencies for positive n spanning a dense subspace. So if you have a set of functions that span a dense subspace, we say that these functions are total in the Hilbert space under discussion. And so in this case here, that would be L2 mu. And so I have some tea for keeping my voice going. And so here and it's actually a corollary of the classical theorem. So how do I show that the En functions are total? I just take an F in L2 or mu, and then of course FD mu is a sign measure. So I take an F in L2 mu, and then I assume that it's orthogonal to the Fourier functions En. And that means that the measure FD mu must be absolutely continuous by the classical F&M Ries. But if mu is singular, that can only happen if F is 0 as an element in L2 or mu. So that is a direct, fairly easy corollary of the classical F&M Ries. But then the other question is, for your specific fractal measures that you built, you want to know what the generalized Fourier basis functions look like and how to construct them, their properties, and we'll get to that later. Okay, and so historically, there's been a lot of effort in going into extending F&M Ries from one dimension to higher dimensions, and a corollary of our discussion is such an extension. And so I'll do that on the next page here. And so this is a definition, and this definition for measures that are built in more than one dimension. And so, for example, on the square here, but it works much more general on product spaces. And then obviously, if you're in more than one dimension, singular doesn't really tell you very much, because there are many ways you can be singular. But this one here is a specific way that a higher dimensional measure can have singular properties, and we call it slice singular. And the reason for this is that it's defined from two things that you do in probability theory for measures in higher dimensions. One is a marginal measure. And so if you're in high dimension, then you have coordinate projections, there's a random variables, and they have probability densities, and those are called the marginal measures, and that's number one, and I call it Xi. And you can also think of it as the pullback using the coordinate projection constructed from the initial measure mu. So I'll show you some pictures what they look like. And then the second one is a rigorous construction of conditional measures. So for every x, you look at pi 1 equals to x as a subset of the product space, and so then from probability theory, also called also a more sophisticated version of probability theory that goes by the name Rocklin. There's a family of conditional measures indexed by the points in the x-axis if we build a conditional measure in the x-axis, and they satisfy the Bayes rules from probability, but extended to this math theoretic construction. In other words, the direct integral of the conditional measures with respect to xi would give you back the measure mu that you started with. And so if both of the measures, number 1 and number 2, are singular, number 2, they have to be singular for almost all x, of course. If that is satisfied, then we say that the product, the measure mu on the product space is slice singular. I want to emphasize that the measures that we're interested in here would never be product measures. In probability theory, you know that no one cares about product measures because that just giving up correlations. You want to study more fine-tuned details of measures, and that includes the conditional measures. And so that's the definition of a slice singular measure. And now I'm ready to, so that was definition 2, and this is that's their number 3. And that is, you can think of that as a direct extension of the F&M Rees to 2 dimensions. You can go to more than 2 dimensions, but then you have to do an induction with slices in each of the conditioning. And what it says is that the Fourier frequencies for a 2-dimensional frequency variable in the quarter plane here, they span a dense space in L2 or mu if mu is slice singular. And the way to do it is to use the direct integral decomposition that I mentioned in in definition number 2, and then use the 1-dimensional case and put together a direct integral, and you get the condition satisfied. Of course, this only says that that these special quarter plane Fourier frequencies span dense, but the next step, and that's the main thing that goes in my talk, is to how to create generalized Fourier expansions based on having a good system of total functions like this. So that's the next term here, and then finally now I'm able to give you some pictures. And you probably have seen them. These 2 pictures here go by the name Sierpinski. The first one is Sierpinski triangle, and the second one is Sierpinski carpet. And those of you who have seen IFS measures will recognize that the maps that we iterate come from scaling. For part A, you scale by a factor of 2, and you leave a gap in each scaling step, and then as you continue, you get the Sierpinski gasket, and the gasket is the limit object. But you also rescale the measures, so there will be a unique self-similar measure supported on that Sierpinski. And in the part B, we scale by 3, and we leave a gap that looks like a square as opposed to a triangle in each step, and we continue here. And so you can see that they have a good chance of being slice singular, and the answer is yes, they are. But it's a bit tricky. Now, obviously, if you've worked with Cantor constructions, you will see that all the conditional measures, the so-called slice measures, are Cantor measures because you have gaps for almost all x. And that can be made rigorous. So that's the easy part. Now you look at the x coordinate, and you see that you have the whole unit interval for the x coordinate, and there's no gaps. So then you tell to yourself, how can that be singular if there are no gaps? Aha! There's an important theorem about IFS measures, and that is that you have to look at not only the scale and the gaps, you also have to look at the weights that you use at each step in the iteration. And so if you look at the marginal measure in part A, then you see on the first half of the x interval, you have a double weight because there are 2 pieces in the support of mu, and then the second one you have a weight 1, so you have weights 2/3 and 1/3. And so then that implies that this marginal measure xi here is mutually singular with respect to the Lebesgue measure. And I'll explain that a little more as we continue. It relies on a beautiful theorem of Kaptani that I'll get to. And so the same for the other one, for the x in unit interval in the x coordinate is divided in 3 pieces, but there are no gaps. However, the first one has weight 3, the second one weight 2, and the last one weight 3, and therefore the weights are not uniform, and therefore the marginal measure in the x coordinate is mutually singular with respect to Lebesgue measure, and therefore both of these famous IFS measures are slice singular, and therefore our Fourier frequency functions in theorem number 3 would span a dense subspace of L2 of these IFS measures. And so I'll give you other examples later as we continue here, but I want to make sure that I don't get too much behind. I think it's better to include all the details in the beginning, and then I can go faster later on. Obviously, if you increase the dimension, you have the same thing, but then you have to define slice singular inductively because you can slice by subspaces of dimension less than 1. So I'm not going to repeat the definition of slice singular, but you can sort of guess what it is by doing induction on the dimension here. And so now I get to the other things here. And frame is generalized Fourier basis, and projection refers to Hilbert space, and Casimir is a particular algorithm that you can build using projections, and I'll explain that in a moment. But before I do it, maybe I'll just remind you of the baby algorithm. That's where you start with a vector. You start with a matrix equation Ax equal to b in linear algebra, and then for vector x, and then the matrix equation is given by hyperplanes, and then you start with a vector, and you make an orthogonal. You drop an orthogonal to the first hyperplane, and then an orthogonal to the second hyperplane, and so on. And for each hyperplane, the orthogonal vectors are given by the last line here. And what we mean by that is that it's the difference between the successive vectors xk and xk minus 1. It's the difference between these vectors that would be orthogonal to the hyperplanes. And that's illustrated in this picture here. X0, and you drop the perpendicular down to the second hyperplane, and you get then the difference x0, x1 is orthogonal to that, and then you drop onto the first hyperplane, and then x1 minus x2 is orthogonal to that, and so on. And now you do that for any system of projections, but for the moment, I'd look at a sequence of projections given by a sequence of vectors, and so in that case, we talk about one-dimensional projections, but later we'll discuss others as well. And so you can see the orthogonality property that we talked about here. For the discussion here, I would often find it convenient to identify a subspace with a corresponding projection, and then the orthogonal complement of that subspace would be identified with 1 minus p. So if p comes from V, then 1 minus p comes from the orthogonal complement to V. So that's what it looks like in pictures. But in the algorithm, it's actually much easier. So look at 3 and 4. And the algorithm that I just showed you in a picture can actually be expressed in the language of operators this way here. Why? Because 1 minus p, if p0 is onto the subspace v0, then you start with a vector and you do the projection onto the orthogonal complement of v0, and then you get a new vector, and then you do the projection onto the orthogonal complement of v1, and so on onto the last one, which is an iteration on the previous vector projected onto the orthogonal complement of Vn. And so the picture that I showed you a minute ago in part B here is exactly what is written out in the algebra of the language of projections, and that refers to any Hilbert space. But I mentioned that we have fractal Hilbert spaces in mind, in particular, and so I want turned out that we want to build systems of vectors, and this one here is consistent with what we do in other iterated function system multiverse solutions. You iterate a system like this, and then there's an extra one that tells you the difference between what you did in the previous step and the next step here. Sometimes we refer to that as resolution and detail. So you can think of QN as an extra detail in the tail end of the previous one. And they look like now innocent enough, but if you write out the algebra of those, then you discover that the algebra of the TNs and the QNs should remind you of what we call frame systems in Hilbert space. So frame systems are generalized Parseval systems, so they're not orthogonal, but they have a Parseval property. And so I'll translate the properties that the two systems have on the bottom half of the page. I'll translate that into what's called a Parseval system here. And the corollary number 6 is testing whether we can build up a Parseval system that fills out the whole Hilbert space. Well, we can only do that if the sum of the Parseval operators, as you add them up, will be the identity operator on the Hilbert space, because that's what it means to be total, to have a dense span. And so those are conditions 1 and condition 2. But the corollary coming directly from the previous slide here, especially the very last equation, is that this property that's rephrased as number 1 and number 2 is equivalent to saying that the tail operators Tn go to 0. So that means that you get more and more Fourier functions. So the leftover, the error term, goes to 0. And that's the role of the two iteration systems, the T systems and the Q systems here. And I'll say more about them later here. And also I'll say more about the references here. So the 3 letters here, I'll discuss them at the end of the talk. From my co-authors, and the J, of course, is myself, right. And so here we mention the distinction between strong operator and weak operator. Turns out, under very mild condition, all the convergence properties will be, in fact, in the strong operator topology. Okay, so now we're ready. If you hit a vector in your Hilbert space with the QJ operators and add it up, then you get a Parseval representation. Why? Because the QJ vectors, QJX vectors, satisfy the Parseval property. So you get for every QJ system, you get Parseval representations in your Hilbert space like this. And the only thing that's required there is, of course, that it's total, which means that the Tn operators should go to 0, so that all the resolutions suffice for filling up the whole Hilbert space. So that's that. The next one here is super important. So that it comes from the P's and the Q's. But remember, I said that the main application I have in mind would be where the P projections come from a sequence of vectors. That means each P projection is a projection onto one-dimensional subspace spanned by the E vectors. And now I hope I don't have to apologize for using Dirac notation. Dirac was a pioneer in quantum theory and in the use of Hilbert space, and he was very efficient with notation. He said that if we have a bra ket as an inner product, then we should also have ket bras, and ket bras would be the corresponding rank 1 operators. And so Pj would be a rank 1 projection, and Qj is constructed from the Pj's the way I explained it. But remember that involves this extra twist in the algorithm here. So in addition to the EJ vectors, you get a new sequence, GJ, and the new sequence GJ is then giving you a rank 1 operator like this. And if you hit a vector in the Hilbert space with Qj, then you get the inner product between Gj and X times the EJ vectors. And if you add them up, you get a generalized Fourier expansion. And that's one reason I'm a great fan of Dirac's ket-bra terminology for finite rank operators like this. But the main vectors we're aiming for here is the G vectors, and they turn out to be the Fourier functions that go into our Fourier representations as we continue here. But how can we use the Q's and the P's to directly construct these new vectors, the G vectors, in the application we have in mind? The E vectors would be the Fourier vectors, and then the G vectors would be the Parseval build out from those Fourier. Now, keep in mind, the Fourier vectors are not Parseval, but the G vectors are Parseval, and that is good enough for building a Fourier representation. And so if you translate the definition we talked about here, then you get the following recursive relation for the G vectors. It can be made a little bit better if you move the sum with a minus sign on the right. If you move that to the left, then you get an infinite gram matrix that hits the G system and gives you the E system. And that infinite gram matrix is fairly easy to invert. And so that would give you a more direct formula for the G functions in terms of the E functions. But remember, the application we have in mind, the E functions are the Fourier functions. Okay. And now I go back to the general formulation we talked about, which was a frame representation. And I would say that number 15 is especially important. So if you apply number 15 to L2 or mu, then you get, and the EJs for the Fourier functions, then you get an honest Fourier representation for L2 or mu. But this one here is a little more general because it applies to any Hilbert space. And but in the case of the fractal measures, we will have a very detailed piece of information about the G functions, and I'll get to that shortly. But you see that the G functions satisfy the Parseval property, which is what the last equation is telling us. And you can hit the equation with an operator, and you get another Parseval representation. And so putting all of this together, here you get that the E system is effective if and only if the G system is a Parseval frame. But don't forget that the E system may not. In fact, for the middle third Cantor set, the E system is not a Parseval system, but the G system will always be a Parseval system. So that means that for all of the examples that have been studied earlier, including the ones that are considered difficult, and the one that's considered difficult is actually in middle third. My first paper was for the Cantor 4, where you divide by 4 and have 2 gaps and iterate. For that case, we could build an orthogonal Fourier representation, but for the C3, there can be no more than 3 orthogonal Fourier functions. So for other examples, you can have an infinite Fourier system, but no infinite system might be effective, and so on and so forth. That's true for the Sierpinski triangle, by the way. Okay, so we'll continue here. This is just a reminder about the slice singular property that allows us to create these generalized Fourier expansions. And so having said that, I then introduce this probability discussion that I mentioned, which is that when we have such as an algorithm here, then you can actually let the algorithm be a stochastic process. In that case, it'll be a stochastic process taking values in projections, and they're fairly easy to construct. I have earlier worked on operator-valued Gaussian processes and so on with many applications, and so this would be an example of such a stochastic process taking values in projections. And when you have such a process, there will be an expectation that you apply to an operator, and you'll have a probability density if you have a random variable C taking values in projections. Then the right-hand side of 19 is just the density of these projections here, and so the last estimate here is the estimate that's required for being able to build a Fourier representation that's valid for almost all the projections coming from such a generalized expansion here. And so here we're back to our old friend, the TNs and the QNs, but now they are random variables. And then we want a conclusion that would be true for almost all of these projection-valued stochastic processes. And the estimate in the previous slide was that if the estimate 20 is satisfied, then you get the total property for almost all relative to that probability space here. And that's relevant for a number of applications, especially for frames that are built from probability constructions here. And this is saying that your convergence would happen in L2 of your probability space. And the application is Pete Casazza, who studied as such measure theoretic frameworks as what he called fusion frames. So generalized basis systems are often referred to as frames, and that's a terminology that goes back to engineering. People probably don't quite agree on the definition of what a frame is, but just think about it as a generalized Fourier expansion, and that'll be good enough for our and so these fusion frames are useful for signal processing, where you get conclusions to be valid for almost all relative to your projection-valued stochastic process. And the name for those fusion frames or measure frames. And so the previous theorem applies directly to that framework. By the way, I should say that Pete Casazza was a pioneer in frames and applied mathematics, and sadly he died a month ago. Okay, and again, we can do it slightly more generally if the process takes values in contraction operators, and we can do the Q and the T construction and get the same conclusions. And so that was for that. And the next thing here is another piece of harmonic analysis, often going by the name of the polydisk and the Hardy spaces here. And so the Hardy spaces are built from the polydisk, and then the popular it's a popular tool for helping us understand the corresponding measures mu. But what do we mean by the pairing between L2 or mu and a Hardy space here? Well, we'll think of the support of mu as being the boundary of the polydisk. So the boundary of each copy in the polydisk is an interval, and so if you do a Cartesian product of these intervals, that would be a candidate for the support of one of these measures here, and so this one here is really a handy way to tell us precisely when we can get these Parseval frames. The easy one is the last line. It says that if you have a Parseval frame and then define an isometry as V of f with f lying in L2 or mu, then that would be isometric from L2 or mu into the Hardy space. And but the converse is true as well. If you give me any isometry V from L2 or mu into the Hardy space, then I can apply the adjoint to that isometry. That's called a co-isometry. And I can V star, and I can apply that to the monomials, the generating monomials in the Hardy space. And lo and behold, that would give me such a Parseval frame Gn. So there's a good amount of literature, and I'll mention later, that studies how singular measures can be understood from subspaces of the Hardy space. In one dimension, the singular measures correspond to inner functions, so that there would be d equal to 1. So this one here is an extension of Berling's theorem for d equal to 1 to higher d. Okay, so that's that. But not only that, we can also write down what these operators look like. This is the Zigel kernel for the polydisk. And when we integrate, then we get a Cauchy transform, and it can be written this way here, and or this way. And the other thing we said is that anytime you go to higher dimension, you have to do the conditional measures here. And the last line here is an example of what we call Bayes rules, that a measure with conditional measures has a unique disintegration formula here as a generalized orthogonal expansion. And so that is relevant for this one here, because what you can now do is you can do a Cauchy transform for both the marginal measure C and for the conditional measures, but they depend on X. And so you have to be a little more clever. You start with a function in two variables, and then you do the Cauchy transform with the marginal measures. That depends on X. And then you do the other Cauchy transform from, no, conditional. So conditional depends on X, and the next one would be the marginal one, and that would be the combined Cauchy transform for any any slice singular measure that we do here. And so that means that whenever we do such a construction here, we get a rich choice of Parseval frame vectors for L2 or mu. So that was what that is. And John Hare is the H part here, J is myself, and W is Eric Weber. So those are two of my co-authors. And we have work on higher dimensional Fourier expansions like this. And so I want to mention that. And now I can finally get to some examples here, IFS constructions. So I mentioned them in the pictures with the Sierpinski before, but this is a little more general. You give me any system of contractive maps with some specified index. Often the index is a set of translations. And then generalized Cantor set is a set W that satisfies 3-2. And then if you give me any system of weights for the set B, then I can do the infinite product measure that was invented by Kakhtani. And one of the theorems of Kakhtani is that if you have two such infinite product measures, one with P and one with P prime, then they're mutually singular. If and only if P is different from P prime, the other Cattani theorem is called the dichotomy theorem. Any infinite product measures, even more general like this, when you compare them, you would have a dichotomy. Either they're mutually singular or they are equivalent. And so that's a property that we will need in order to understand the generalized IFS measures that are built using by a system of contractions and a choice of vectors here, P. The standard IFS measures, you have equal weights, so a fair coin for the probability that you assign to each of the pieces that make up the contractive system. And so this is one of my favorite formulations of what we mean by an IF measure. You can think of the right-hand side as an operator that's acting on probability measure, and you can think of 34 as a fixed point property, and it's easy to see that you can show existence of such a fixed point by being careful with the metrics on you use on the set of probability measures. So those and so again you see that that if you have one IFS with weights P and another IFS with weights P prime, then the corresponding IFS measures would be mutually singular. And that's what happened in the application that I showed you in the beginning for the Sierpinski pictures. This one here is a little more general. That's where we identify the points in an IFS from an infinite sequence of addresses. And if it's contractive, then the intersection of these iterated maps is a singleton. And that means that this intersection then defines a random variable on these product spaces. This is what 37 is saying. And and this one here is simply then saying that the IFS measure is the probability density of that random variable. So the random variable is the one that assigns a unique point to every infinite system of addresses. And so again, remind you of the definition of IFS in the last line here. And this is the definition of the standard support of these measures here, which are called generalized Cantor sets here. And this is that they're mutually singular for distinct weights as an application of the Cattani theorem. And then finally, I get to the Sierpinski constructions again, but built now with another algorithm, a random power series algorithm, and it goes like this. We can build these Sierpinski constructions and see that they're slice singular using what we just did in the beginning of the talk here. So I said d equal to 2 here. Here is just a silly little example showing that a measure in 2D can be singular without being slice singular. That's easy. And this one here is our Sierpinski. And so you have the contracted maps scaling 2, and I write it as a scaling matrix. And that's the Sierpinski triangle written in the right angular coordinate system. And so it fits into what we just talked about in this case here. There are 3 maps, and we'll give the 3 maps equal weight. So there's the picture here, and each step you scale by 2 and leave a gap in the middle, and you continue that. And in the limit, you get the Sierpinski cascade, but you also can rescale the measures. And so in the limit, you get the Sierpinski measure like this. But this one here is a way of making precise that random variable that defines a unique point in this case in 2 dimensions here, corresponding to an infinite sequence of addresses. And the way you can think about that is a generalized dyadic expansion for the points in the Sierpinski. So you can think of 44 as a generalized dyadic expansion. But we do different weights, as I mentioned in the first picture in the beginning of the talk. The first one gets double weight and the second one single weights. And so you can generate these examples using Markov chains by iterating figure number 5 here. And as I mentioned, the weights are equal weights to each of the 3 pieces in the Sierpinski, and that's equation number 40. And then having done that, here you can do the Fourier transform of 46 here. And then, of course, you can do the Fourier transform of any measure, and then you get mu hat. For these measures are compact support, so mu hat would actually be an entire analytic function, which is useful for the study of the detailed properties of these fractal measures here. And so all these fractal measures here, if you iterate 47, you would get that the Fourier transform would be an entire analytic given by an infinite product representation, which is important. You can also do IFS measures in the for measures supported in the complex plane. The famous Fatou measures and Gaston-Julian measures are typically constructed by having the branch maps being the branches of the inverses of an analytic function, even a polynomial. So the IFS construction here applies to many more examples than I just mentioned here. The examples that I alluded to from complex geometry sometimes are called complex dynamics examples. And so I mentioned that. And so now we go back to the Sierpinski gasket example. And what you see here is that we get a generalized dyadic expansion, but the x-coordinate, remember, has weights 1/3 and 2/3, and the y-coordinate has right. So the thing I mentioned about unequal weights, 1/3 and 2/3, is the one that's responsible for why the marginal measure is mutually singular with respect to the Bank measure. And so that's that. And this is just writing out the Kaptani construction for the infinite products with unequal weights here, responsible for why we get slice singular measures for the Sierpinski constructions. Yeah, and here's another picture of the same thing here, where you iterate and use these different weights at each step. And so it also gives you a random variable representation for the points in these Sierpinski sets here. Okay, and again, we build the Markov chain the way we talked about it. As you move down here, you get you get an infinite diagram with two vertices, and the first vertex can go 2 places, and the second vertex can go only 1 place, and then you iterate these Markov diagrams, and you get another representation, and the Markov transition matrix we talked about is the one that you see in the first line here, and that has Perron-Frobenius vector on the left, which is the one we just talked about with the unequal weights. So the unequal weights correspond to properties of the Perron-Frobenius in a Markov chain like this, and that's what it looks like in a picture as you built these examples. This one here is in 3D. It's one of my favorite examples. It's the fractal Eiffel Tower I constructed. Actually, the funny thing is that many of the Sierpinski examples in 2D typically do not have an orthonormal basis of Fourier frequencies, but this Sierpinski Eiffel Tower here, in fact, does have an ONB consisting of 3-dimensional Fourier frequencies, and they can be constructed explicitly. For some of the possible, it's typically more difficult to construct explicit, but here we're in 3D, and so we build up the Markov representation of this fractal here that I called Eiffel Tower fractal. So in that case, here you have 4 pieces and you have 3 coordinates. Each coordinate is scaled by 2, and you have the IFS with equal weights, but the marginal ones have unequal weights, 3/4 and 1/4. And again, we do the Markov here, where we build up the Markov chain this way here, and so you get a transition matrix as the one in the middle here, 2/3 and 1/3, and you get Thorne-Frobenius vector with 3/4 and 1/4, and you get this Lie singular property that we talked about. This one here is a conjecture, and the conjecture is saying that what we saw in the last 2 examples here is probably typical. So what it says is that we get that the generalized Fourier functions here would be total in L2 or mu, if mu is one of these IFS measures here, if and only if the Perron-Frobenius vector is not uniform. So if and only if the Perron-Frobenius vector is not proportional to the equal weights. So you see in these cases, we have total, and in this case here, the Perron-Frobenius vector is consistent with the conjecture here at the end. And so that was one thing here, and here's some of my the first one is a pioneering paper on IFS, and the next one here is one of my joint papers with Dorian Dutkai, where we studied particular Cantor constructions and their basis properties. And the HEDA is a beautiful book on the kind of probability theory I need here, including the Kaktani construction. And here I have my 2 co-authors, John Herr and Eric Weber, and we have some papers here, one contemporary math, dealing with frames and this kind of harmonic analysis, and another one building with the Sega kernel and polydisk representation, and one that deals with these generalized Casimir algorithms and the corresponding infinite products of projections. And here we have Kaktani with his theorem about dichotomy. And then finally, the beautiful book by Donald Saracen on the Hardy spaces. So I think I'm probably out of time. I'm happy to take questions now.
Okay. So, any question to the speaker?
I'll go back to some of the pictures so
Yes.
that you can better visualize some of the complicated equations we talked about. And the transforms and the examples and the probability spaces and the Parseval systems and the G functions. The G functions come this way from the P and the Q constructions, and we get this magic system of vectors G, the Parseval system here, as coming directly out from knowing that the Q systems will be rank 1 operator. The P's are projections, but the Q's are rank 1 operators that are not projections. And and here's the algorithm again, just to remind you. And again, this is some summary of some of the papers that I mentioned that in fact appeared in the literature, and the algorithm itself, and more of these Sierpinski pictures. So is it a good place to stop?
Yes. So if there is no no question, right?
Hey, sorry,
William,
Professor.
yes.
I have a
question about theorem 3.
Yes.
In
Excellent. Yes.
yeah.
Excellent.
In this theorem, you say that if mu is slice singular, then you can
Yes.
conclude that the Fourier
Yes. Yes.
is dense.
Yes.
But
Yes. Yes.
the condition is necessary.
Ah, that's a good question. We think the answer is yes, but we've not proved it.
Okay. Sure. You think that this is
So
true?
because you see in one dimension, F and M Rees, it's if and only if. And so we think that it's also true in higher dimensions, but we haven't proved it yet.
Okay. Thanks. I also have another question about do you think that when we for the middle third countermeasure,
Yes.
we
Yes.
know that there is no Fourier orthogonal basis,
Yes.
but you think it should have a
So
Fourier
this,
frame?
yes, so the main theorem I'm presenting here, in fact, applies to the middle third. And what it gives you is a Fourier expansion with the Parseval being the G system. And so I'll go back to that, mention it here. Yeah, here you go.
Yeah.
So apply equation 15 to L2 mu. And let EJs be the Fourier functions and GJs the Parseval I talked about, and then let the vector x be an element in L2 of mu. Then what this says is that you get an honest Fourier representation in every such singular measure mu, and that includes the middle third. And so the thing that's different from this construction from the earlier attempts, that people who worked on it earlier desperately tried to get the E system to be Parseval, and that turned out to be very, very, very difficult. And so what we're doing is we say, to get an honest Fourier representation as number 15 here, you don't care whether the E system is Parseval, as long as you can get a dual system G that is Parseval, then 15 is an honest Fourier expansion relative to the norm in the Hilbert space, or if the Hilbert space is L2 or mu, it's an L2 or mu representation, and it's so actually you can in fact show that it converges almost everywhere itself. Not, you don't have to go to a subsequence for these fractal measures here, and so the Parseval property, if you look at the last line, refers to the G system and not the E system. So that's an excellent question. Yes.
Okay, thanks very much.
Is there any more question from the participants? So
I
no more
want to
questions.
thank you for your kind attention, and to the organizers with the invitation, and to the excellent questions from the audience. I'm very grateful.
Thank you, Palle, for giving a nice talk. So there is an announcement. Our next talk will be next Friday. It will start in the same time. So Professor Peter Mesefast from Technical University of Munich, Germany, will give the talk. So his talk will be on fractal interpolation and quaternions. So see you again on Friday, December 12, GMT time, 3 p.m. At the same time it will start. Thank you all.
Very much. Thank you.
Bye. Take
Thank
care, all
you.
of you.
Thanks very much. Yeah, thanks. Yeah, bye-bye.